So we'll move into a slightly another theme here. I'm going to talk about how to optimize buildings. We build building in order to be inside the building, and therefore it's really important that we get the right indoor climate, both temperature but also daylight. So therefore I'm going to talk a bit about that. I need to find out how to this one. So. First of all, what I'm going to show with this example is that we want to evaluate the performance of different kind of solar shading systems based on indoor climate, daylight, and also a view out. Usually, or typically, when talking about indoor climate and energy, we do take dynamic shadings into account. But when we talk about daylight, it has been a tradition not to include them simply because we have been evaluating based on what is called the daylight factor, so the fraction of daylight that comes into the building. But now we have actually got a new European standard on daylight in buildings. And this standard enables us to actually take into account also dynamic shading in the evaluation of the daylight in the building. So of course we should include that because that is what real life is. And then as the last one, we also want to evaluate the view out. And that's simply because that is one of the most important things for the occupants inside the building, that they can have a view out, follow how the weather is outside, and so on. So why is it that we have developed a new workflow to do this? That is because the typical workflow for evaluating building like this has been that you have had one engineer who has been doing all the thermal simulations. So they have set up their own model, their own geometry with weather data and window and shadings and a control strategy for dynamic shadings. And then they have been doing this simulation, get some outputs. And then another engineer, maybe even another company, they will do the daylight simulations because it's two different programs, so they don't speak together. So they will build up their own geometry again. They will hopefully use the same kind of weather data, but then they will have another definitions of the window and shading system, and usually only they have been using static shadings. If you have had a dynamic shadings, they have not been included. So which means that they have no control strategy. So of course, these are actually two different buildings that you are trying to simulate. So one for thermal and one for daylight. And we just end up getting a lot of hot buildings. And that is what we are seeing today. A lot of these new buildings where you have done design of them with low energy buildings, we actually see that they all get too hot. So of course we want to improve this. So we want to use the same assumptions when you're calculating on one building, so that you use same assumptions both for the thermal simulations but also for the daylight simulations. And in this way, if we use the same assumption all the way around, we will be able to get good working buildings. The goal of this workflow that we have developed is that we want to have a workflow that is relying on the same assumptions, both for indoor climate and daylight simulations. We also want to make it easy to use so that everybody can use it, and not only for the experts. And then we also want to make it time efficient. When you do daylight calculations based on climate data, it usually takes a really long time. But we want to see if we can increase that speed so it doesn't take so much time. And then of course we want to have a high accuracy so that we can trust the results that we're actually getting. So this workflow that we have developed, we have been using it to evaluate the performance of different solar shadings, but it can also be used in other areas of building simulations. If you want to investigate some special parts, you can do that. You can simply output the things that you want to. So, and just to mention, BPC stands for Building Performance Chart, because we can actually use the data that comes out of this workflow to assess the whole performance of the building indoor climate-wise. So the same assumptions. Yeah, we only want to have one geometry definition, so it means that we define the geometry only in one place. So if updates come in the projects, you always have updates to the projects and geometry, and you only need to change it one place. We don't want to change it several places because then errors will happen. So the geometry definition is only one place. And then the weather data, of course, we want to use the same weather data for both the indoor climate simulations and daylight simulations. And then in order to use the same window and shading definitions for both types of simulation, we want to use the angular optical properties of the glazing. And this can be captured in what we call a BSDF file, stands for bidirectional scattering function. And this is the figures that you see up here. So it basically tells you something about the incoming light, how is that transmitted to the glazing in all angles. And in this way you can have a really precise description. Usually we only use the LT naught value or the G naught value, so we usually only take what is perpendicular to the glazing. But here we can actually take into account that the sun is actually not in a normal position to the window. Usually the sun will be in other positions for the window, and this is in this way we are able to capture that effect and make a more accurate calculations of what we will actually get inside the building in the end. And then, of course, we want to have the control strategy of the dynamic shading system. We want to use the same for both the thermal calculations and the daylight calculations. So the workflow that we developed, we used Rhino and Grasshopper to create the geometry. We use EPW weather data files. And then we use Lorne Berkeley's program called Windows, where you can build your own glazing and make these BSDF files that can be used in the programs. And the control strategies, we also build them up in Grasshopper. And by using Grasshopper, we're able to do parametric statics, so we can vary all the things that we want to vary. It can be the building size, the window size. It can be different control strategies, whatever we like to vary. And for the calculation engines, we use Radiance for the daylight simulations, and we've used Energy Plus for the thermal indoor climate simulations. And then for the data handling and output, we have used Honeybee. We have chosen to evaluate these parents based on European standards. So for indoor climate, we use EN 15251, and on the daylight, we use a new European daylight standard, EN 7037. So just to give you an example of how this workflow can be used, as I said before, we evaluate the indoor climate. We are looking at the annual operative temperature inside the office. So it means that how many hours a year will we have more than 26 degrees inside the room. For the daylight, we use illuminance level inside the office. So we say all the hours that we have more than 300 lux at work level. We need to have that in more than 50% of the daylight hours, in more than 50% of the area. And then for the view out, we look at the view out class according to the standard EN 14501, which is a standard that classifies different aspects of solar shadings. And then we combine this with the number of hours that the shading is actually activated. So in order to have a broad variety of shading systems, we have a low energy glazing just for reference, 3-layer. Then we took 3 different solar control glazings. Then we had 2 types of micro shades, micro lamellas. Then we have 2 types of screen, one with a transmission of 5% and one with a transmission of 14%. And then we have Venetian blinds, where we tilted the lamella either 30 degrees or 45 degrees. You can also see some example of the pictures over there. And just to give you an idea about how these are performing. I talked about these BSCF files where you can see not only the normal values, but also the angular values. And in this, So in this graph, you can see the transmittance in the visual spectrum. So over here you have the light transmittance, and of course this is the light transmittance at 0, which is the value that we usually get. But here you can actually see the angle dependency of each of the shading devices. And the top ones here, those are the solar control glazing. They are also having an angular dependency. Then we have the micro shades. Those are here. They are very angle dependent. And then you have the screens. Those are the two down here that have a really, really steep curve. And that's, of course, because they have really steep lamellas and broad lamellas. Then we tried to simulate two different office types, and a multi-user office and a single. Single in this case you have 4 workplaces, but a smaller office. We also took in all the details of the window geometry, so we took that into account. And then we varied the window to flow ratio from 10% and all the way up to 40%, meaning that mostly the entire facade was glazed. And then we wanted to see how these different shading options were performing in different climate zones. So we took, you can see far north, Trondheim, Oslo, Copenhagen, Stuttgart, Madrid, and then Sydney, just to have somebody on the other side of the world to see how would that perform in this climate. And then, because we could do this parametric variation, we also took 16 different orientations, so we covered everything more or less. And then we ran the workflow and did more than 10,000 simulations, both on indoor climate and daylight. And of course, this is a really, really huge material, so I can't show you all of that. So I've just picked out one location for you to see. So if here I've shown Stuttgart, south facade, with a window to flow ratio of 40%, which means that it's the whole facade that is more or less glazed. And in this case, we can see, I have to go here. These are the solar control glazings. The limits here, the red line here is what the standard says is you should have a maximum of 100 hours above 26 degrees. So everything below that red line is good. That's meeting the indoor climate standard. If it gets above it, it's not. So what we can see here is that some of these solar control glazings, they're not really strong enough to meet the indoor climate requirements. The blinds here at tilted 30 degrees, they have a threshold here of 50 watt per square meter. They get just above, so you would say, okay, they more or less pass. It's really small. The reason for these not being the same thresholds is that we tried to pick out the ones that were actually fulfilling the requirements, which means that if you take a higher threshold here, the number of hours will go up. If you take a lower threshold, the number of hours will go down. But these are all meeting the requirements. If we then look at the daylight, we can see that and here the threshold is, I should say, here the threshold is 50% spatial daylight autonomy. So 50% of the time, with 50% of floor area with more than 50% of the time at 300 lux. And here we can see that almost all of these investigated solutions, they meet it, except for this screen. It just hits the 50%, this 5%, 250 watt, but the one that actually has a transmittance of 40% cannot meet it because the thresholds. It's not meeting the daylight standard. So that doesn't work. And then if we look at the weighted view out, we can see that these static shadings, they, of course, they are not 100%, and that is because we are taking into account the view out class according to the classification standard, and they all have a view out class, what you call class 4, which is very good. But it means that it needs to be multiplied with a factor, because it's not a totally clear view. So they have a weighted view out of 85%. If we then look at both the blinds and the screens, because their view out classes, they are much slower. You have a less view through the blinds and through the screen. They do not meet this requirement of 80% weighted view out at all. So what you can see from this is, well, yeah, you can meet the thermal indoor climate, and you can meet the daylight with most of these solutions, but the compromise here is really the view out. So with this workflow, we managed to establish a workflow that really relied on the same assumption. So we use the same assumption for both daylight and indoor climate. It's really easy to use. You can press a button, then it runs. And we can run like thousands of simulations if we want to. It's also time efficient. I mean, if we have to run that many simulations, it cannot take several hours every time you do a simulation. So the longest simulation is approximately 4 minutes for both the daylight and the indoor climate simulation. And it has a high accuracy. We take the angle dependency of the glazing and the shadings into account. This workflow, we are going to make, sorry, that was the wrong button. This workflow we are going to make available on our website for download, and also we are currently working on doing some tutorials on them. So we hope that after the summer break, we will be able to have this material on our homepage, simply for download, and everybody can use it and learn how to use it by looking at the tutorials. And also all the results that this workflow is generating, we are going to present online. We have a new calculation tool that is called SimShade, available on our website already. And all the results from this workflow is going to be available simply in this calculator, so that you can go in and choose your room size, your window size, type of shading that you wanna compare with, and then you can see the performance both on the thermal side, on the daylight side, and how much time is the shading activated. So what is this weighted view out? So, yeah, thank you for your attention.
Thank you, wonderful presentation. Are there any questions from the audience?
Thank you. That was excellent and huge amount of information there. My query would be, did you look at the winter condition where the solar gain might be seen as beneficial to reduce heating costs?
Well, we do a yearly calculation, so we calculate for every hour of the year. So we do not only look at, you can see, well, what I presented here was temperatures over 26 degrees, yeah. But you'll be able to look at also temperatures below whatever you want to, or whatever other measure you want to look at. So a part of this is also to look at the energy use. I didn't show any results of this, but in our calculator SimShade, you will be able also to see the energy usage for heating and for cooling, and see the peak load for cooling and stuff like that.
But this would be used for normal office size space, presumably for big volumes like your one with the roof light. You wouldn't be using it for that because of stratification effects.
Yes. Yes. So right now this workflow is only, I mean, you saw the two different office types. Those are the two that we are calculating right now. But of course it will be able to make other room types that we could do also. But we have to start somewhere.
Thank you very much.
Are there any, excuse me, are there any other questions? I actually have one. You mentioned a source for the weather data.
Yeah.
I'm not familiar with that. I'm familiar, based in the U.S., with the NOAA, the Aeronautical Association. It's a government-based. So how is that data collected? Is that a website that's available to everyone for use?
It's actually American data. So yeah, it's available from my website, and it's very common to use that for calculations like this.
Is it based on averages per day, or is it got more of an hourly look? Or?
It's hourly. It's hourly weather data. So all the calculations here are hourly, yearly hourly calculations.
It's a 4-minute simulation, so that's...
Sorry?
It's a 4-minute simulation?
It takes 4 minutes to run the calculation.
It's pretty incredible.
Yeah.
Yes. Well, if there are no other questions, thank you. Wonderful presentation.
Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.